Hello, in this lecture we are going to study the Carnot cycle. We have already done the topic on the heat engines and the refrigerators. Today we are going to talk about a thermodynamic cycle which is called as a Carnot cycle. So Carnot cycle is nothing but it is a theoretical, or you can say ideal, thermodynamical cycle. So it is a ideal or theoretical thermodynamical cycle, and it was proposed by Carnot and Nicholas. So whenever some work is done, it must be converted into some sort of energy. So conversion of work into heat is an irreversible process. And what does the heat engine want to do? Heat engine is just partial reversal of this process. So what does heat engine would do? Heat engine is not. It is involved with the partial reversal of this process. That is, heat engine would want to take heat from certain source and would want to do certain work. In ideal case scenario, as you are aware, there is something called as efficiency. We have already discussed efficiency in the previous lecture. So higher the efficiency, the better the engine is. So in today's lecture we are going to derive the expression for efficiency of the Carnot cycle. Okay, so in general we know that whenever heat flows in an irreversible process, it results in a finite drop in temperature. So in Carnot cycle, the engine takes heat from a heat source. So in a Carnot cycle, what happens that the engine or the working substance takes the heat from the heat source, and what happens is, what is idealized, that if the temperature source is maintained at T1, so whenever it takes heat, this engine should also be maintained, the engine temperature, or I should say the working substance temperature, should also be at T1. Similarly, when engine rejects heat to the sink at the lower temperature, then during this rejection of heat, the temperature of the sink and of that of engine should remain the same. So whenever your engine rejects some engine, or I can say working substance rejects some heat, during the rejection of the heat, the temperature of the sink and that of the working substance should remain the same. Okay, so the cycle is ideal only if the engine does not exchange any heat during the process when its temperature is changing. Okay, so I'll write it here so that you can remember. The first point I want to mention is that in this ideal case scenario, what we are going to consider, that when engine takes heat from heat source, at, let's say, temperature T1, the temperature of working substance or that of engine should also remain at T1. So there is no such gradient in temperature, so there is no such change in temperature. Similarly, when engine rejects heat to the sink at a lower temperature, let's say T2, then during this rejection of heat, engine also remains at the same temperature. At the same temperature as that of sink. So in other words, I'm trying to make a point that these are the conditions for an ideal setup. That is, an ideal engine is one uh, where engine does not exchange any heat during the process. So it is an ideal process is what? Ideal process is one when engine does not exchange any heat during the process when its temperature is changing. So if it is not exchanging any heat, it implies that delta Q is 0. Or in other words, when I'm saying that I'm accepting the heat, when my engine is accepting the heat from heat source, they both should remain at the same temperature. And when the engine is rejecting, or the working substance is rejecting any heat, then it should be this at the same temperature as that of sink. So basically, every I can say ideal cycle, or every for Carnot cycle, if I want to say that in the case of Carnot cycle can be thought of series of events or series of adiabatic and isothermal process. So I can write in a single line that every process in the idealized Carnot cycle must be either isothermal or adiabatic. Okay, so now we are going to see that how Carnot cycle is like what are the different steps involved in the Carnot cycle. Now we are going to see the different step in the Carnot cycle. So an ideal Carnot cycle is accomplished in 4 steps. So there are 4 steps. I'm going to write those 4 steps and then we are going to see what they are. The first is that the working substance expands isothermally. So in first case, the working substance expands isothermally. And how does it expand isothermally? By absorbing heat. So it involves absorption of heat and absorbs heat Q1 from the heat source and maintained at T1. Now in the second scenario, what happens is this working substance expands adiabatically, and during an adiabatic expansion, as we know, the temperature would drop ideally. So until its temperature here the T2 is the temperature of the sink. In third scenario, this working substance is compressed adiabatically, compressed isothermally, so sorry about it, compressed isothermally and T2, and when it is compressed isothermally, this particular heat engine, or you can say the working substance, rejects heat Q2 to the sink. And again, the working substance is compressed adiabatically, and when it is compressed adiabatically, the temperature rises, and for a complete cycle to be completed, it is compressed adiabatically so that it achieves its initial state. So it is compressed adiabatically back to its initial state. At temperature T1. So if I have to represent it on an on a PV plot, so what I'll do, I should write it better 1, 2. So I'm writing it as process 1, then 2. This is my process number 3, and this is my process number 4. So in the first process, the working substance is expanded isothermally. So whenever there is an isothermal expansion, so it has to be via absorption of some heat source. So basically, I know that the first process will be explained by an isotherm. So I know isotherm will be some this kind of variation. So from A to B, the gas expands isothermally. So it will attain a temperature T1. So I'm just with dot, I'm just writing the temperature. So this is T1. This is the temperature of the source. Now in the second process, as you are aware, that there would be an adiabatic expansion. So when adiabatic expansion takes place, there is a temperature drop. So I'm drawing it by an adiabat. So this is my adiabat, this is an isotherm. So first process is represented by an isotherm AB, and then followed by an adiabat, which is BC. And during an adiabatic expansion, the temperature drops, and this temperature drops to T2. This T2 is the temperature of the sink. Again from C to D, in the third process, you are aware that there would be an adiabatic compression. There would be an isothermal compression. So in isothermal compression, heat would be rejected to the sink by an amount Q2, and now you reach a point D. It is at the same temperature as that of sink, and from D to A, I can write that again my working substance would be compressed adiabatically, so that it again reaches back to its initial state T1. So basically, again, if I can write, my gas starts from state A, there would be an isothermal expansion up to state B, and in this process heat is absorbed. In this entire process, heat is absorbed. And you know that during an adiabatic process, the change in terms is 0. So whatever work is done in this particular process AB, it is equal to the heat absorbed. It is equals to the heat absorbed. And what is the work done? So it is from I have already derived all these things for you. It will be, if there are n moles nRT1, ln of volume at B divided by volume at A. Okay, so this is your work done in the first process, which is equal to the heat absorbed. So basically, this would be at B. I know my state variables would be PB and VB. So this is VB and PB. And similarly, at A, I can write my state variables to be VA. This is a P versus V plot. Okay, so this is how I'm explaining it. When I'm talking of, so this will be my VC, PC, and this would be VD, VD. Okay, so in the third process, in isothermal compression, what would be the work done? So work done during an isothermal compression would be the heat exchanged to the sink, or heat rejected to the sink, and it will be equals to nRT ln of VC upon VD. Okay, so when I'm not writing a negative sign, I've simply written VC by VD. Okay, so this is heat rejected to the sink during an isothermal compression. Oh, so sorry, it will be T2, sorry, nRT2, because this is taking place at temperature T2. Now, when we are talking of adiabatic process, last time in the previous lecture, I have already discussed the equation of state. In fact, we have derived equation of state. So now when we are involving temperatures and volumes, what I would do, I will write a equation of state in terms of T and V. So in adiabatic process from B to C, one can relate the equation of state as T1, because at temperature at B the temperature is T1, volume VB raised to power gamma minus 1. This is an equation of state for the adiabatic process. At B it is, at C it is T2, VC raised to power gamma minus 1. And similarly, when I am moving from D to A, in the case of adiabatic compression, so it will be T1 VA gamma minus 1 is equals to T2 VD gamma minus 1. So if I want to see what is my VB and what is the ratio of VB to so that I can do here. So what I'll do, I'll simply divide it. So what I'll simply get VB divided by VA raised to power gamma minus 1 is equals to VC divided by VD raised to power gamma minus 1, and simply I can write that my VB by VA is equals to VC upon VD. I hope it is clear. Since heat is rejected to the sink, it will be written negative. So what would be my Q2 by Q1? So let me write my Q2 by Q1. Just give me a minute. Okay, so let me first write the modulus part of it, so that at least things get so Q2 by Q1 would be simply equals to NR T2 ln of VC by VD upon NR T1 ln of, sorry, if I am not writing negative, then it will be VD by VC, sorry. Okay, this will be equals to VB by VA, and since I know that VB by VA, when heat is rejected to the sink, so basically what happens is, if I'm writing this this particular expression, that is work done in adiabatic process, no, work done in, sorry, isothermal process, I know the work done in isothermal process is what? It is equals to NRT ln of V final upon V initial, right? V final upon V initial. But I had accounted for heat, negative heat already, by writing it by VC by VD. If you understand what I'm trying to say, see what happens is, if I'm talking of work done during an adiabatic process, it is nRT V final upon V initial, but I already written VC by VD. Why did I write it VC by VD? Because it gives me the total absolute value of Q2. But actually, when heat is rejected to sink, heat should be negative. So basically, I should write it as nRT ln of V final, which is VD by VC, because VD by VC would inherently be would be less than 1. So the log value would give me a negative. So I had written VC by VD so that I can write the absolute value of Q2. So in general, I will write this. This will be VD by VC. So this will give me what? This will give me minus T2 by T1. Okay, because this NR cancels, and I know that VC by VD is equal to VB by VA, so I'll write it by VC by VD, a negative sign, so it will be minus T2 by T1. Okay, so Q2 by Q1 is simply, or rather I should write in mod, so Q2 by Q1 modulus should be equals to what? It should be equals to T2 by T1. T2 by T1. As you're aware that the thermal efficiency of a heat cycle, as I already derived, it is equals to 1 minus Q out upon Q in modulus. So eta is equals to 1 minus, what is Q out? Q out is Q2 upon Q1 mod, and it is certainly equals to what? It is equals to 1 minus T2 upon T2. So what we are getting is that the heat efficiency of a Carnot cycle depends only on the temperature of the source and the sink. Sorry, the temperature of sink here, forgetting it, and T1 is the source. So basically I will write that the Carnot cycle, the efficiency of the Carnot cycle, I'll write it here. The efficiency of the Carnot cycle depends only on the temperature of the source and sink. Depends on temperature of heat source and temperature of sink. It is going to be large if the ratio is small. Okay. Okay. So what we want, if we want to have a large you can say efficiency, we would want that the difference between the two should be more. So basically if I want to write eta is what? It is T1 minus T2 upon T1. So if this is large, so my heat efficiency will be more. So basically this heat efficiency would be large when the temperature difference delta T between the sink and the source is large, and is very small when this temperature difference is small. So all these things you can write in your sort of university exam. Now there's another way of looking at it, and we can look at it using the TS diagram also. We have already covered entropy in our previous lectures. So if I want to write it in, if I want to make the diagram in TS space, what it would be? So for an ideal gas, what will be isotherms? So basically if I'm talking of isotherms, so in TS, so it will be replaced by a straight line parallel to the x-axis. So if I'm talking of isotherm T at T1, so this will be replaced by a my straight line parallel to the x-axis. So the first case when we drew an isotherm in PV plot, now I'm drawing a T1, this straight line as an isotherm in TS curve. The second state was when I was moving from A to B. I was doing an isothermal expansion at temperature T1. From B to C, the working substance was expanding adiabatically so that it reached the temperature T2. So when I'm moving from B to C, I know that delta Q is 0, and if delta Q is 0, my ds would be 0, so my entropy is a constant. So I'll draw a plot like this. From C to D, the working substance was compressed isothermally at temperature T2. So again it will be represented by a straight line parallel to x-axis in ds curve. And from D to A, there was an adiabatic compression. So for simplicity, what I'm going to take, I'm going to calculate the net entropy change during this cycle. I want to calculate the net entropy change during this cycle, and for simplicity, let me take that number of moles is equals to 1. So in the first process, the gas absorbs a heat Q1 reversibly and is allowed to, in the first process, I'm again writing, the working substance accepts heat Q1 from the heat source reversibly and is allowed to expand isothermally. allowed to expand isothermally from, let's say, volume, if I maintain the same notations, VA to VB, and in this particular process the change in entropy would be simply equals to Q1 by T1. So this is my first case. In the second case, the gas or working substance is allowed to adiabatically expand. When adiabatic expansion is taking place, the pressure falls. Okay, in terms of pressure, if I want to write, when gas is expanding isothermally from VA to VB, in this particular scenario, the pressure decreases from PA to PB. So there is a decrease in pressure. Because volume is increasing, so pressure would decrease in an isothermal process. In adiabatic process, the same happens. The pressure falls further from PA to PB to PC now. So there is a fall in pressure. Since it is an adiabatic process, so there is no heat exchange between the system and surrounding. Since there is no heat exchange, according to the first law, we already know that my temperature falls. Falls from where to where? From T1 to T2. So my temperature falls, but since there is no change in the heat, so there is no change in the entropy, and I would write that my delta S2 would be 0, or simply my entropy remains constant during this particular process from T1 to T2. And mind you, I am talking of reversible processes. Okay. Third, in the third scenario, the gas which is at temperature T2 is now compressed adiabatically from C to D. So in the third process, again I'm saying adiabatically, I'm so sorry, isothermally. So now there is an isothermal compression involved at temperature T2, and which leads to the reduction in the volume. So now my volume reduces from Vc to Vd. And in this process, the change in entropy delta S3, if I'm saying heat is rejected, if heat is rejected, and let's say the heat rejection takes place is around Q2. So in this particular process, when the working substance isothermally compresses from C to D at temperature T2, there is a reduction of volume involved from Vc to Vd, and there is a heat lost. So heat lost, I'm taking a negative and negative, so this will be minus Q2 upon T2. So change in entropy would be minus Q2 upon T2. This is in the third process. In the second process, delta S2 is 0. And when in the fourth process, what happens, the gas is compressed adiabatically from D to A, so that it reaches the initial volume and the pressure. As a result, the temperature restores back to T1, and in this time also, since there is no heat exchange involved, delta S2 would be, delta I should write S4 should be equal to 0. So what is happening in the fourth process? The gas is finally restoring back to its original positions, restoring back to original volume and pressure. As a result, if it is an ideal case, so now original temperature is also restored. But in this particular process also, entropy remains conserved, because you know it is an adiabatic compression. So in adiabatic compression, what happens, delta Q is 0, so my delta S4 should be equal to 0. So since there is no heat involved in this particular, no heat exchange between the system and surrounding, so delta Q is 0, therefore delta S4 is 0. Since we are talking of an ideal Carnot cycle, so an ideal Carnot cycle, so Carnot cycle is reversible. So Carnot cycle in ideal case is reversible. It implies what? For reversible process, the delta S should be equal to 0. And what is delta S? Delta S is comprised of delta S1, delta S2 plus delta S3 and plus delta S4. It all should be equal to 0. It implies what? it implies that Q1 T1 should be equals to what? It should be equals to Q2 T2, and it simply gives you that Q2 by Q1 is simply equals to T2 by T1. And another way of expressing the heat efficiency is net work done by the heat engine divided by initial heat absorbed from the heat source, that is Q1. So it will be equals to Q1 minus Q2 divided by Q1. So it will be 1 minus Q1 by Q2, so 1 minus T2 by T1. So if I look at this particular scene from the perspective from the entropy change, the heat efficiency again turns out to be 1 minus T2 by T1. So again, this heat efficiency depends upon the temperatures of the source in the sink. Again, larger the difference between the source, the temperatures of the source and sink, larger would be the heat efficiency. Another thing that you need to understand, that eta in any case would be less than 1. Eta in any case would be less than 1. Okay, now another scenario one can think of, that what if T2 is equal to T1? If T2 is equal to T1, then eta would be equal to 0. Okay, so what does this interpret? It interprets that if T1 is equal to T2, if there is no such temperature difference between the source and the sink, then we cannot operate any cycle. So one I can write, we cannot operate a cycle, Carnot cycle. What does that mean? We cannot convert heat into work if there is no gradient in temperature, if there is no change in the temperature. Okay, another important thing is, this one must remember that the efficiency, since it depends on T2 and T1, so efficiency of an ideal Carnot cycle, so Carnot cycle is an ideal case, is independent of the nature of the working substance. So all these important things you should keep in mind while understanding the Carnot cycle. I hope all these lectures are benefiting you. Please let me know if there is any doubt. Till then, take care. Bye-bye.